Hello, my name is Sharon Godfrey, and I will be presenting predicting flight hours as part of Data 670's capstone project status presentation number 3. Today we will be going over the problem scope, data set overview, data insights, data format, predictive models, model algorithms, model results, and lessons learned. Looking at historical flight hour data to predict flight hours is the basis of the project. The proposed problem is the PMA is looking to budget for their next POM cycle and needs to know how many flight hours are going to be needed over the next 5 years, broken down by year and month. There are 3 TMS type model series that is going to be the CH53 Kilo, the CH53 Echo, and the MH53 Echo that will be needed to be budgeted. A predictive model will be created in Python to its highest level of achievable accuracy to assist the PMA in forecasting their flight hours over the next 5 years based on a month-to-month basis. Several metrics and visualizations will accompany the project to include correlation matrix to identify variables that increase or decrease flight hours. And the analysis includes relationships identified between variables and target variables to include manpower needed per flight hour, which will give the PMA an extra information for their POM budgeting. In this project, 2 data sets are used to predict for the future flight hours of the H-53. The first data set, flight hours, is a time series that contains 76,512 entries and 17 variables that span across 2016 to 2022. Each entry is of a single flight completed by a specific aircraft, in this case, the 53s. The specific model of the H-53 is defined as well as the specifics of the flight, including the date, purpose, and hours. The date of the flight is included in the data set and is broken down into a year, a quarter, a month, a day, and its completion date. The last piece of the flight entry contains the flight mission information that is broken down into a general and specific purpose, including a description of the mission. And the last flight detail contained in each entry is the total flight hours completed by that specific aircraft. The second data set, which is the maintenance man hours, is a time series that contains 166,220 entries and 37 variables that span across 2016 to 2020. The maintenance man hours data set contains details in each entry of the man hours associated to each H-53 aircraft, and each entry of the single work unit code, which is also known as a WUC, with all associated man hours for that specific WUC. This type of H-53 model is not defined in this data set, but does have each aircraft serial number associated with the work unit code. The work unit code has an associated date, year, month, day, hour, and completion date for the man hours included. The dataset also includes if the maintenance man hours were on a weekend or on a holiday. These 2 datasets were merged together to create the FIN dataset, FIN_DF, which is for the final dataset, which merged together on the BUNO and on the date, created a much smaller dataset with only 45,003 entries, but increased in variables to 52 variables. Upon cleaning the data, the final data set resulted in 45,003 entries and only 34 variables. And 9 of those variables were from an object and moved into a string. Taking a look at our cleaned data set, we ran a few plots on it just to get an overview of what the data looks like. The first time series plot displayed in the top right figure has the flight hours broken down by variable by month, quarter, and year. This figure illuminates some interesting areas in the time series, particularly where the flights drop in January and April of 2017 and March of 2019. Initially, the thought was that the flight hours would decrease in 2020. However, it does not appear to be enough data in 2020 to determine if a decrease existed. The duration of a flight appears to have been steadily increased across over the time. The second time series graph which is going to be in the middle, displays the flight hours based on a TMR, which is a total mission requirement description variable. There were a total of 5 values in the TMR description group for the variable, which included a log, SPT, a support, training, combat, and BGO. The descriptions represent the logistic support, the support services, training, combat, and operations. The BGO and the combat account for less than 1% of the flight hours, and the top 3 variables are only used in the figure to show the flight hours. Logistics support has the highest duration of flight hours, with an average about 4 hours per flight, followed by training around 3 hours per flight. And then support services around 2 hours per flight. The training flight duration appears to stay above 3 hours. This is potentially due to a training flight in a syllabus needing a minimum of 1.5 hours for a sign-off, and to maximize sign-offs in a training environment, 3 hours of flight is needed at a minimum for 2 sign-offs. The logistics support hours seem to hover around 4 hours per flight, and this is likely due to fuel being the limiting factor. Longer flights can occur in a CH-53 Echo, but expansion tanks would be needed for these types of flights. The last time series graph in the bottom right corner is of the maintenance man-hours per entry for the month and year over the span of 2016 to 2020. Initial assumptions for the maintenance man-hours would be that they increased over the years. The CH-53 Echo is an old airframe, and as an airframe gets older, more parts break down and the supply chain has a harder time acquiring parts for an outdated airframe. However, the opposite is shown, where the maintenance man-hours per entry decreased over the years. Now that our data has been cleaned and processed, and we've had a quick overview of our data set, we need to go ahead and put the data in the correct format for our predictive models. A couple steps that need to be taken is feature engineering, simple lagging, encoding, scaling, doing our training and testing split, and cross-validation. Feature engineering is the process of selecting and manipulating and transforming data into usable features for predictive modeling. During data transformation earlier in the code, for a total of 11 variables went under transformation. Since the initial transformation, 9 of those variables have since been excluded from this data frame. One variable remaining was the depart date and time. This variable was needed to be transformed one more time into a new name, which is now going to be called date, where the data set could be grouped together by this variable. Simple lagging was performed on the target variable, TMR hours, for rolling features to better inform the time series. Lagging is a way to transform the time series flight hour data set into a supervised learning problem. The lag feature shifts the target variable, TMR hours, to appear as if they have occurred later in time. Encoding was actually not performed on the flight hour dataset due to categorical variables either being transformed or removed due to relevance. Standard scaling was performed by using the sklearn standard scaler in Python on 12 numerical columns in the dataset. Scaling is performed on step modeling to normalize the data and eliminate any bias outcome of predictions in the accuracy rates. The data is split into a training and testing split, and then ran into cross-validation. Cross-validation is where the data, cross-validation method was ran on the data, and training and testing splits are measurements are taken only at a specific point in time. Since this is a time series data set, one cannot apply a random selection without resulting in a sequence missing a lot of values. This is where the cross-validation method comes into play on the training and testing set. The cross-validation method does a repeated training test evaluation. Rather than making one train test split, it makes multiple. In this case, we did 4 fold validations, and this was because there's 4 years in the data set. The training and testing data sets contained only 874 entries and 153 entries. The number of entries appears to be smaller than expected, but this is due to the TMR hours being grouped by date and work unit code and reduces the number of entries. The training set is based on the first 3 years, and the testing data set is based on the last year. And the testing data set will appear to be smaller, but that's due to it not being a full year of 2020, where it is only actually 6 months of data. Now the data is in the correct format and can be available to run the predictive models. There are 5 predictive models that were run on this project: the linear regression, neural networking, which is an MLP regressor, the k-nearest neighbor regressor, random forest regressor, and support vector regressor. The package in Python used to run each of these models is going to be using the sklearn package. Linear regression is used for identifying the relationships between variables and forecasting a target variable. The neural network model identifies complex patterns in the data set by using hidden layers and nonlinear activation functions. The k-nearest neighbor regressor is a supervised learning algorithm for regression that predicts the correct class. And the random forest regressor is an ensemble method for regression that functions by constructing several decision trees. And the support vector regression is a supervised learning algorithm used in regression analysis. Each one of the models listed in the previous slide were compared, but their model algorithms are what's compared in this slide. And those are compared on the following metrics of the mean, standard deviation, variance, and coefficient of variance. The mean, which is the average of the flight hour data and is used to determine if a bias exists in the model's predictions. The standard deviation is a measure of the amount of variation or dispersion of a set value. A low standard deviation indicates the values tend to be close to the mean. In contrast, a high standard deviation indicates the values are spread out over a broader range. The standard deviation predicted values helps understand if the dispersion of the values in different models, the lower the standard deviation value, the lower the chances of overfitting a model occurs. The variance is the measure of how far observed values are spread out from the average, or mean, of predicted values. A high variance indicates values are further from the mean. The coefficient of variance is the ratio or relative dispersion of the standard deviation to the mean. A low coefficient is ideal for making it easier to measure accuracy. These metrics are important in determining whether the regression models are accurate or misleading. When looking at the algorithm results to determine what model would be the best to run in the regression analysis, the ideal model has a high mean, a low standard deviation, a low variance, and a low coefficient of variance within the range of 4 to 6. 2 models that are automatically not ideal are the KNN and the SVR models. The KNN model has a very low mean, high standard deviation, variance, and coefficient of variance, while SVR model has a low mean, high standard deviation, low variance, and negative coefficients of variance. The most ideal model algorithm moving forward is the random forest regressor. The random forest regressor model produced 6 metrics. It's going to be going through the explained variance, the mean squared logarithmic error, R squared, mean absolute error, and the mean squared error, root mean squared error. The explained variance shows the inconsistency between a model and the actual data. A high EV between 60 and 100 is ideal for a good model performance. The MSLE is the ratio between the real and predicted values. The smaller the value, the better the model results. The R-squared metric informs on how well the model performed and is also known as the coefficient of determination or the goodness of fit. The closer the R-squared value is to 1, the better the regression of the model is. The MAE is an average absolute space or distance between the true data and predicted data. And the MSE is the average squared difference between the estimated and true values. Both MAE and MSE metrics work best with lower or minimal values. The RMSE is the squared root of MSE and is the standard deviation of the prediction errors. The lower the RMSE, the better the regression model. These factors are the performance metrics of a regression model. As we can see, the random forest regressor model was run on the test set, resulting in the following results as can be seen in the slide. We have a very good R squared and we have a low RMSE, making this a very good model. Just a few quick lessons learned. One of the biggest one was time management. Data cleaning and transforming was very time consuming, and Python was not as intuitive as I had initially thought. One of the things that really made this difficult was the learning curve on it. I had never done a time series in Python before, and it created a very challenging environment and a learning curve that I wish was not occurring within the capstone itself. If anybody has any questions, please feel free to reach on out. Thanks. Bye.